Hello friends, welcome to the today's lecture on calculus of variation. If you see, we have discussed in previous lecture the concept of functionals. So here we started with the definite integral I of y defined as x1 to x2, f of x, y and y dash d of x, and we have seen that the value of this definite integral is depending on the function y of x, and which is a function of x here. So we can say that this definite integral can be considered as a map from this function y to the value I of y. So it is kind of, say, I of y can be considered as a function of this function y, and which assign the function y to the value denoted by I of y. So we can consider this as a function which whose argument is function itself. So this is the concept termed as functional, and we have seen that the calculus of variation is a particular branch of calculus of functionals, in which we try to discuss the method to find out the extremum and extremum values of these kind of functionals. So here we can say that the problems which involve the calculus of variation were first considered in around 1696 and became an independent mathematical branch after the fundamental work of Euler in around 1737. Now we try to discuss certain problems of calculus of variation, which is supposed to be say beginning point of the classical calculus of variation. In fact, it is the work of John Bernoulli. He posed a problem in June 1696, and that problem is known as the problem of Brachistov-Kron problem. So that we are going to discuss as follows. So the first problem which he discussed is this, that the object is to find out the curve connecting two specified points A and B that do not lie on a vertical line, and possessing the property that a moving particle slides down under the influence of gravity and having no friction along this curve from A to B in the shortest time. So it means that let me just give you a small idea here. So here we simply say that we have a 2 point A and B, and they lie in a vertical plane, not in a vertical line. They are not either on the same level or not a vertical line, and we try to find out, say, the curve connecting A to B. So here let me write it B here. Okay. So we try to find out that if there is no friction along this curve y, let us call this as y as a function of x here, and then we take a particle on this starting from this A, and just under the influence of gravity it start falling along this curve AB, and we need to find out, say, this function y equal to y of x, along which this particle takes the least time. In fact, Brachistov means shortest and Kron means time. So it is a problem of shortest time, or you can say that this is a problem of quickest descent, and this problem was posed by John Bernoulli in 1696 and solved by John Bernoulli himself, his brother James Bernoulli, Newton, Leibniz and L'Hopital, and it turns out that the line of quickest descent is a cycloid, and the lying in the vertical plane and passing through A and B. If you remember, the cycloid, and it is not a straight line connecting this A and B. It is something like a cycloid connecting these point A and B. Though this line, straight line, is a line having say least distance between A and B, but this is not the curve along which this particle will take a least time. Rather than it is the cycloid which takes least time between A to B. So you can consider that if we have to find out a curve which is having say steepest say curve near A, so that we have a greater velocity near A, and then it can reach to point B in a shortest time, and it is turned out to be that it is coming out it is turned out to be that this curve is your cycloid. We will discuss this problem, Brachistochrone problem, in a separate lecture. And the second important problem is the problem of geodesics, and in this problem the object is to determine the arc of minimum length connecting two given points on a surface phi x y z equal to 0. So it means that we have a surface phi x y z equal to 0. For the time being, you can consider that the earth is the surface, or you can say that we have a sphere and as a surface, and we try to find out say the minimum distance between 2 points and the of lying on the same sphere. So here we have a surface and there is a 2 point on that surface, and we try to find out say minimum distance between these 2 points, and we can say it like this. So here we have a surface like this, you can take anything, and then we have a point A and B, and we try to find out say minimum distance between the point A and B, and in a way such that this curve will also lie on the surface. So here we can say that we are minimizing this functional, which is j equal to x1 to x2, and this nothing but surface patch between x1 to x2. We can say that if we denote this as say x1 y1 z1 and it is x2 y2 and z2, we can consider that this is your you can find out say line integral between A to B, and this is given as j equal to say point between say this A to B. So A to B d of s. Now d of s you can find out as here under root 1 plus y dash square plus z dash square d of x. So here you can say that the we have to find out the minimal of the functional j from x1 to x2 under root 1 plus y dash square plus z dash square d of x, provided that this y of x and z of x are subjected to the condition that it lie on the surface. So it means that phi of x comma y comma z is equal to 0, and such shortest arcs are called geodesics, and this problem was solved in 1698 by Jacob Bernoulli, but a general method, general setup to solve these kind of problems were again given by Euler and Lagrange. So if you remember, this problem is different from the first problem, the problem of steepest descent, in a way or problem of quickest descent, in a way such that here not only we have to minimize this functional, but also that the curve which minimizes this functional is also having satisfying certain other boundation, that is that curve has to lie on the surface phi x y z. So we can say that it is kind of a connected functionals, or we can say that this is the problem with say certain constant. Okay. So here we have to minimize this functional provided that it satisfy the certain given constant, that is your x y z is related by phi of x y z equal to 0, it lie on the surface here. So and next problem is very important problem, is the isoparametric problem. In this problem the object is to find a closed line of given length L bounding a maximum area S. So here it means that we have a curve whose length is already given to you. So here we have a curve whose length is already given, say L is given to you, and we want to find out in a way such that it encloses a maximum area. So it means that we try to find out a closed curve bounded by this arc, and we try to find out a surface having maximum area. And if it is known from the ancient Greece time, then such a arc is basically a circle. So circle is the solution of this, whose parameter is known to us, and it encloses the maximum area. So we can say that, let me pose this problem in a way that one has to find the extremum of the functional S bounded by the closed curve r equal to r theta of given length. It means that we have to find out, say, extremize the area functional. So this S is basically the area of the say region bounded by this this r equal to curve r equal to r theta. So here this is the area 1 by 2 0 to 2 pi r square d theta. So this is the area functional, and we have to maximize provided that the length of the arc which is 0 to 2 pi under root r square plus dr by d theta is square d of theta. So keeping this L as fixed, we have to maximize this, and it is coming out to be that this is nothing but your circle. So here these type of conditions are called isoparametric, and the general method of solving the problems with isoparametric conditions were given by Euler. So this is also similar to the second problem, that we have to extremize maximize this function provided a given function is constant, given functional is constant. So we try to generalize in calculus of variation, we try to generalize the concept presented here in a variety of ways. So one way is just now we have seen that functional x1 to x2 f of x, y of x, y dash x, d of x. So we have seen certain example based on this, but this can be generalized into these following ways. So in second, we may consider a problem or functional which involves not only the first derivative but the nth derivative of the function y of x. So this is another functional which involved the nth derivative of the curve y. And similarly, so we can say that this is the functional which involve only the first order derivative of a function y of x, and this is the functional which involves the first order derivative as well the nth order derivative of the functional. And we can generalize it further, we can say that this function is not only depending only on one function, but it is also depending on the n number of functions. So here this is the functional defined which depend on several functions. So we can say that it is x1 to x2 f of x, y1x to ynx, and its derivative here. So here this is the functional depending on several functions, and we can further generalize in which this single integral is replaced by multiple integrals. So here your variable or argument is a function of x variable, function of more than one independent variable. So here this function is depending on, say, z of x y, where z is a function of x and y. So here your function you can define as this double integral f of x y, z of x y, and its partial derivative with respect to x and y, dx dy. So these are the generalization of the functional which we have discussed just now, that is x1 to x2 f of x, y of x, y dash x, d of x. So mainly it is a functional which involve higher order derivative of argument, and it say involve several independent functions, say y1 to ynx, and this is the problem in which your argument is replaced by, say, a function of several independent variables. So here we want to it is given that this function f is already given, while the function y, y1, ynx and zxy are argument of this function f. Okay. So now let us discuss the study, let us discuss the basic concept involved in calculus of variation. Here it is to be noted that this calculus of variation, which is the branch of calculus of function in which we have to maximize or minimize the functional, and it is closely related. We will see that it is very say closely related to the analysis in which we discuss the maximum and minimum values of functions. So what we try to do here in these coming slides, we try to recall the definition from the calculus, classical calculus, and then we try to see what is the relevant or what is the analog version in calculus of variation. So first thing is to discuss is the function. So function, if you remember, it is a correspondence between a variable independent variable x to a given point. So we can say that a variable y is said to be the function of a variable quantity x if for every value of x, of course this x is ranging over a certain range where this y is defined, there correspond a values of y, and is that value we can denote it as function of x. So here in function, so here this function is basically given any x, you relate it to f of x. So from x we are going up to f of x, and if we look at the several variable means x1 x2, so we can write it x1 x2 and so on xn, then we can say that this f is giving a set of values from x1 to xn, it relate the value of these points to f of x1 x2 to xn. So here we can say that function is kind of a function correspondence between a point to another point, which is denoted as f of x. So here in, if we talk about function of several independent variable, here we can say that it is a correspondence which relate the given x1 to xn values, given values of x1 to xn to a definite value f of x1 to xn. So if we define function and in analogous version, here we can say that in place of x, which is an independent variable, now we take a functional say a y of x, and we say that your functional, this for the timing let me relate it to z of y here, and we say that z of y is a correspondence which relate the function y of x to the value z of y as a function of x, right. So here we can say the variable z is said to be a functional dependent on a function y of x if for each function y of x, of course this function y of x is belonging to certain class of functions on which this z is defined, they correspond a value of z and denoted by z equal to z of y of x. So here please recall here that here x is defined over a certain range, and here in functional this argument y of x is defined on a certain class of functions. So we will discuss some example of certain class of function. For example, we can consider this class of functions as set of all continuous function or set of all continuously differentiable function and so on. So that we will discuss. So we can say that in function it is a correspondence between a point to f of x where x lying in some kind of a range. For example, I can consider this x belonging to a to b, and we can say that f x is a correspondence for all values of x which is defined here to values here. Similarly, functional is a correspondence from a given function from y to z of y of x, and here we can say that y is a function, continuous function from a to b, or you can consider y as a function of c1 function from a to b. We will discuss what is this c and c1 ab. This c1 ab denote the functions which are whose first derivative is also continuous. Okay. Now what we try to do here, we try to see that how these functions and this function are related. So let us consider a particular example, and we try to understand the relation of functional and calculus of variation to the problems of classical analysis. So, in classical analysis we will discuss function and maximum minima of the functions. So, here we try to say how this functional and calculus of variations is related to that corresponding terms. So, what we try to do here, consider this functional j of y which is defined as a to b f of x y dash d of x. Here y dash is dy by dx, and this function y is satisfying this condition that y of a is equal to a and y of b equal to b. So, it means that, so here we have a curve, say y of x, this is y of x here, and this is x equal to a and this is x equal to b, and the corresponding functional is defined like this: a to b f of x y dy by dx and d of x. And we try to find out the relation of this functional to the functions in classical analysis. So, what we try to do here, we truncate this interval a to b into n plus 1 equal parts. So, here we truncate into these equal parts. And so on. So, here we can say that your x naught is given as a and xn plus 1 is given as b, and rest you can say that x1 which is x naught plus h is where h you can say that it is b minus a divided by n. So, here we can say that you can define the points x naught, x1, xn up to xn plus 1, where x naught is a and xn plus 1 is equal to b. So, we are dividing the length a b into n plus 1 equal parts and replace the curve y of x by the polygonal line with the vertices. So, what we try to do here, we replace this curve by these straight lines, these polygonal lines. Okay. So, we can say we can approximate the curve by these polygonal lines, and vertices is given by, here vertices is given by say x naught and a. Here your vertices, this vertices is given as x1 and the y of x1 and so on. So, here your x of n plus 1 and y of xn plus 1, which is nothing but this is b, and this is your yn plus 1 is given as capital B. So, here we can say that now this curve is approximated by polygonal lines and vertices is already given to us, right. So, now we can say that if we do this, then the approximate we can approximate the function j y by the sum here. So, here we can approximate this as the finite sum here. Here we can simply write I equal to 1 to n here, f of say xi, and y of xi is denoted as y of y, and dy by dx can be approximated by its finite difference, and we can write it yi plus yi minus 1. So, here we can write yi minus 1 divided by h, and you can write it like this, is it okay, and into h. Okay. So, here we can say that this is approximate, this integral is approximated by this finite sum. So, here look at this equation number 3, this is the approximation of the functional, and here we are denoting yi as y of xi and h is xi minus 1. Here each polygonal line is uniquely determined by the ordinate y1 to yn, and what is y1 to yn? It is y1 is y of x1, yn is y of xn of its vertices, and the sum 3 is a function of n variables. Now, here if y is a variable, then this yi is also a variable. So, we can say that here this sum is depending on say n variables, that is y1 to yn. Please remember this y naught is already known to us. Y naught is your capital A, and y of b, which is y of n plus 1, is also known, that is given as capital B. So here this sum will depend only on, say, variables, that is y1 to yn, and we can say that this functional can be written approximated by j of y1 to yn. Here y1 to yn are variables, and j can be considered as a function depending on these variable y1 to yn. So here now we can say that with the help of these things, we can say that we can approximate the functional which is given by j of y equal to a to b fx y y dash d of x as this finite sum I equal to 1 to n plus 1 f of xi yi minus yi minus 1 divided by h, and here we can say that as an approximation the variational problem is now converted into the problem of finding the extrema of the function j y1 to yn. So there this j in the original problem, j is considered to be the functional which depend on this y, but with the help of this finite difference scheme we can say that that can be approximated by extrema and extrema of the function j which the in the n variable, that is y1 to yn. So here we can say that these two are related to each other, or I can say that the finite version of functional is a function in n variables. So Euler used this method to of finite difference to solve several variational problem in a way such that the functional is truncated into a function of n independent variables, and he tried to maximize and minimize of the function of n independent variables, and then he tried to consider the limit as n tending to infinity, and then try to conclude the maximum minimum of the corresponding functional. So here it is this, that he replaced the smooth curves by polygonal lines, and they reduce the problem of finding extrema of a functional to the problem of finding extrema of a function of n variables, right, and then he obtained the exact solution by passing to the limit as n tending to infinity. We can say that this equation number 3, if you pass on the limit as n tending to infinity, then it closely approximate this functional. Thus in this sense functional can be regarded as functions of infinitely many variables. So if you recall, what we have done is that we have approximated the functionals as the functions of n independent variable, and then we can say that as n tending to infinity, we can say that this functional can be treated as a function of infinitely many independent variables. So that is what we are writing here, that in this sense functional can be regarded as functions of infinitely many variables, and the calculus of variation can be regarded as the corresponding analog of differential calculus. Now to discuss the methods for maximizing and minimizing the functional, we need to know certain basic definitions, and these definitions are in an analogous version of the definitions available in calculus, in classical calculus. So we will discuss one by one, and first we try to recall the definition given in classical calculus, and then we give the analog version of the definition in calculus of variation. So first definition is known as increment. So in classical analysis, if we talk about increment, then increment in independent variable is defined as the delta x, and it can be written as the increment delta x of the argument x of a function f of x is defined by the difference between two values of the variable delta x. So it means that if we take x1 as a fixed variable, fixed value, then the difference between x minus x1 is denoted as increment in x. And here if x is the independent variable, then we may recall that differential of x is given by this increment in x. If x is the independent variable, then the differential of x is matching with the increment of the increment in x. So similarly we can define the analogous version of increment in calculus of variation. Please remember here the argument of the functional is a function itself. So here we can say that the increment, or it is known as a variation, delta y of the argument y of x of a function z of y of x is defined by the difference between two function y and the value y1 here, and here y of x varies arbitrarily in a class of functions on which this functional is defined. So here in this in a classical analysis it is just a difference between two values of x, but here in variation it is the difference between two functions. Okay. So here we need to define this variation in a proper way. Now with the help of this increment, now we can define the continuity of a function. So continuity of a function is defined in the sense that if there is a small change in argument of this function f, that is a small change in x, then there is a small change in the function of f of x. And similarly in analogous version we can say that a functional z of yx is called a continuous functional if for a small change in argument, now argument is a function here y of x, there correspond a small change in the functional z of y of x. So it means that if in argument y of x, if we replace another value, say that is y of y1 of x, and there is a small change between y of x and y1 x, then we try to find out whether this difference between the functional is small or not. If it is small, we can say that your functional is continuous. If it is not small, we say that your functional is not continuous. So here we will discuss more thing about how we define the closeness, or how we say that this y of x and y1 x are close to each other, or the difference between y and y1 x is small. So with to discuss this we will discuss certain more things, and that will continue in the next lecture. So here we stop, and in next lecture we will define in precise manner what do we mean by continuity of a function, and discuss certain properties, some example of function which are continuous functional. So here we stop, and we will meet in a next lecture. Thank you very much.